Good evening, everyone. My name is Alex Stewart, and I'd like to welcome you back to another Tech Talk in our series sponsored by Seismic. Today, we have the pleasure of welcoming Saeed Albayrak to give us a brief talk on distributed systems. So, without further ado, I'd like to pass it over to you, Saeed.
Thank you. Thank you. Hey, Alex. Hey, everyone. Thank you for hosting this Tech Talk, and also special thanks to Seismic, our sponsor, for sponsoring this Tech Talk. So, for those who don't know me, my name is Said Albayrak, and for the next 15 minutes tonight, we will demystifying the domain of distributed systems. What is it? What are they? And why they are there? This is a high level explanation of ideas and concepts. We are not going into deep tonight, just a heads up. So grab your coffee or tea and let's jump right in. So, distributed systems, as an introduction, the word nowadays used in a broader, wider sense, oftentimes referring in different meanings. The word distributed in terms such as distributed systems, distributed programming, and distributed algorithm originally referred to computer networks where individual computers were physically distributed within some geographical zones and areas. So this is a terminology breakdown. So if you have distributed systems, what is the opposite of distributed systems, right? We have centralized, we have decentralized, and we have distributed systems. So we are not going into too deep on this, but the basic idea of the centralized systems are one central server manages all the operations. And oftentimes, if you want to do some scalability, you have limited options, and you may want to do some vertical scaling, like upgrading your hardware, memory, CPU units, which is really hard. But on other hand, if you want to if you have some distributed system, it's highly scalable, modular, and it's easier to upgrade as your system grows up, right? So the other thing you may hear in this domain is decentralized system. This is came up little this may sound a little confusing, but the main thing here is that the control aspect of it. Each node controls its own operations, right? This is the main thing to keep in mind when you are talking about decentralized systems. So, in order to tackle this domain of distributed systems, we have a case study. And I think the solving a real world problem question is a better way to understand this concept, right? So, we're going to take a look at the story of Netflix. Netflix is founded in 1997 in California by Reed Hastings and Mark Randolph. Basically, it was a DVD by mail renting company, and as they move on, they grew up so fast, and they started streaming platform, and in in into 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 in 2007 they launched Watch Now, and shifting the focus from physical DVDs to online streaming, which was a huge change in the industry. And somewhere along here in 2008, something happened for Netflix. Something big happened, and they wanted to change everything. And that problem was a database problem. And they had a huge disaster in 2008. They had a major hardware failure, caused a 3-day database corruption, halting all the services and business operations. Basically, company lost around, if I'm not wrong, $3 million ish at that time. It's a not big amount for that for Netflix, but it was a huge lesson. So the problem caused because of Netflix used a monolithic architecture. All services was tied to single data centers. Everything was on-prem, and if one part failed, the entire system crashed. Right. So they came up with a solution, a 7-year migration to AWS and microservices distributed architecture. So why they come up with such a solution? So they studied what was their mistake and why it happened, right? So they wanted to they wanted to eliminate single points of failure. If search service goes down, streaming and login keeps working. And the other opportunity here is the scalability, because they have different types of clients, regions, countries, continents. So they need to be able to scale rapidly. And the other one is agility. Independent teams can update specific features without getting touch or getting touched to another business logic or operations, right? So they come up with something good here. They call it chaos engineering. So when Netflix migrated to AWS, the first thing they implemented is something called Chaos Monkey. For me, this is a engineering miracle. It's a really amazing tool that randomly shuts down production servers to ensure the system is resilient enough to heal itself automatically. So they call it the best way the best way to the best way to avoid failure, to fail constantly. That's their philosophy, basically. So the outcome is completed in 2016. They started in 2008, and they complete the migration in 2016. And this move made the Netflix one of the most stable and scalable platforms in the world. So we have a comparison here. So before, they had a monolithic structure. So one massive code base, on-prem databases, all functions, billing, search, movie recommendation systems, playback service, everything is just one huge code base. But of course, there's a risk to it, and if one service has a bug or some type of problem, everything is gone. And of course, uh, they have speed issue here. Very slow to update, requires a full system restart, reboot for any small change or update. Then the post migration is the new era, the microservices, the structure, resilience, speed comes really handy, and hundreds of tiny independent services. They constantly talk to each other via APIs and gateways. So resilience is the key here. I'm telling this keyword again and again. If one service fails, the others continue to run. And lastly, again, speed, and thousands of daily updates can be made with different nodes, which makes lots easier to handle everything and configuration. So we talked before about this, the Chaos Monkey. The philosophy is the best here. The best way to avoid failure is to fail constantly. We're going to talk about this more. And for me, it's it's a really amazing tool. So the finally evolution, this eventually grew into a simian army. The Chaos Monkey uh, has different subcategories. They have Chaos Monkey, Chaos Gorilla, Security Monkey, Doctor Monkey, Latency Monkey, Chaos Kong. They all configure and manage the whole system, and they randomly shut the system and restart it again. So that's the whole idea. So what's the goal here? The three main goals are HAFT and DR. What are those? High availability, uptime, fault tolerance, single point of failure. If one thing fails, only that thing, that service fails, nothing else. So every other node can work independently, and clients, customers still get something. And there's a disaster recovery, right? Ability to restore as soon as possible. So what is the functional requirements here? Subscription management for the Netflix, right? Allow users to play and pause, rewind, fast forward, offline streaming, and content recommendations. For non-functional requirements, we have low latency, high responsiveness, scalability, high availability, near zero downtime. We talk about here, secure authentication and authorization. Those are pretty simple. There's a lot more to it, but I cannot mention right now because the whole thing take 8 years, and it's not easy to understand. It's not easy to it's not easy to talk a concept that happened in 8 years just in 10 minutes. So then we have a renaissance. This is the final result, the high level system architecture. We're going to take a quick look. And so here, 1, 2, 3, 4, 5, 6, 7. We have the core microservices. We have playback service, catalog service, recommendation service, billing, subscription, user service, analytics, and transcoding. So the core engine of this system is this guy right here, Eureka. This is a service discovery tool that Netflix engineers built. So what it does is when you have a microservice that is live and into production, they have to send some registry to this guy. They tell, okay, this is my IP address and this is my port number, and put it in your registry. I'm alive, and every 30 seconds they have a heartbeat, and they send those heartbeats to this guy and telling them I'm alive, I'm healthy, and you can use me. So this is the main engine. When you have, as a client, you enter from here, right? You have a web browser, mobile, smart TVs. And we have a Zool here, which is a API gateway. Everything enters from here. Then API gateway tells you to where you go. If you want to go to playback service, API, you go to Zool. Okay, I want to go to playback service. Then Zool tells Eureka, okay, this guy wants to go to playback service, and that's it basically. From there, we have a ribbon, which is a client side load balancer, and then we have a Hystrix, which is a circuit breaker. I want to talk this about more, but we only have limited time, so I'm not sure if I can make it on time. And yeah, this is a circuit breaker, and if something happens in the system, it automatically shuts down and pulls the fallback patterns. This is basically a safety trigger, I would say. So from there we have a EV cache, which is basically a memcache system. We have CDN Open Connect. We have Titus, which is a orchestration tool, and we have Archives, which is a config management tool. It manages the config files, static and dynamic config files. And lastly, we have Chaos Monkey. And this Chaos Monkey basically, as I told you, it shuts down randomly, regularly or irregularly microservices, and basically wakes them up again and makes them run again. And that's the general idea. Uh, just a side note, all of those applications are open source. That they are not maintained anymore. I think most of them are retired, and you can use them. You can find them on GitHub, and pretty much that's a high level mapping of the Netflix distributed systems. I don't want to go too deep, but yeah. And yeah, thank you for contributing to this tech talk. And thank you for Seismic once again for sponsoring this tech talk. If you guys have any questions, I can take the questions.
I have a question.
Yep.
So since you mentioned that like recently the systems are very distributed and there are a lot of third-based systems because of this, and it's very complex and its traceability became harder. So because of this reason, keeping the systems compliant is a burden and not easy. So my question is, how do you keep your system compliant and secure?
Uh, that's a good question. Actually, I'm not sure if I can answer on top of my head, but generally speaking, there's some monitoring and analyzing tools, and there's some standards I can recommend. Like I usually recommend implementing infrastructure as a code, so the version is controlled and auditable. And another common thing is integrating security and compliance check to your CI/CD pipelines, and using some benchmarks like CIS benchmarks. Those are the tools and benchmarks I can recommend. I hope it answers your question.
Thanks.
I think there's no more questions, so
All right. Well, if there's no more questions, thank you so much, Saeed. And that's all we have time for anyway. So that timing is perfect. So thank you, Saeed, for that informative talk. Thank you, everyone, for coming out tonight. We'll see you at the next one.